Hello, we are Team ME20. My name is Allison Main, and my partner Trevor Hutchinson and I are working on the project for a MEMS magnetometer sponsored by General Dynamics Electric Boat. This project also has an ECE team with members Daniel Burke, Andrew Peterson, and Zachary Adamson. Our advisors are Professors Dr. Georgios Matthew and Dr. Yang Chow. And our industry sponsors are Eric Holgren and Rob Scala from Electric Boat. Our sponsor, General Dynamics Electric Boat, was established in 1899 and has displayed standards of excellence in the design, construction, and life cycle support of submarines for the U.S. Navy. Our project consists of incorporating a microelectromechanical system, or MEMS, into the circuitry of a magnetometer device to increase accuracy and efficiency while also reducing the size of the device in comparison to what is commercially available. A commercially available option of a MEMS magnetometer is depicted in Figure 1. Our deliverables are to develop a magnetometer model that is able to measure changes in the magnetic field as small as 0.1 nanotesla, develop an analytical model for thermal load, and provide analysis for vibration tolerance based on environmental factors, with the environment being shown in Figure 2. Our team researched several different options for a magnetometer design. We narrowed the options down to the top 5 designs, consisting of a magnetoresistive, Lorentz force, torsional, search coil, and flux gate magnetometer. Using several different criteria, we selected the magnetoresistive option. The ECE team also performed a down selection of designs and came to the conclusion that the magnetoresistive option would satisfy the requirements provided by EB. Based on the Pew Chart's findings, Figure 3 became the primary design since it is a magnetoresistive option. There were other sources which discussed such a design, and Figure 4 was found to fit the requirements of the project. This design uses the GMR effect, which is a quantum mechanical effect observed in multi-layers composed of alternating ferromagnetic and non-magnetic layers. From Figure 4, we developed a model in Figure 5 using the software COMSOL, which is used for thermal analysis by the ME team. Each layer was decided by both the ME and ECE team based on material properties and availability of values of such properties. The ECE team also uses this model, but they vary the size of the contact pads, which are depicted on the top of the model in Figure 5. The ECE team will now present on their analysis of the magnetometer model and some key aspects of their work to provide a full picture of this project.
Hi, my name is Zach Adamson. We started with a prototype on the left, and we ended up with a final design closer to the one on the right. We found that the larger contact pads on the top and the bottom gave more accurate results. So to simulate our magnetometer, we varied By from 0 to 0.5 Tesla in steps of 0.01 Tesla. We applied 1000 amps per meter to our top aluminum contact, and this allows us to test our simulation of a magnetoresistive magnetometer.
Here we have an LT-SPICE circuit diagram that we made to show how we would handle the outputs of one of the 3 magnetoresistors that we would use. We have 3 different source blocks to show how different types of noise can affect the system, but we take the output and run it through an amplifier, a low-pass filter, a buffer, and then an analog to digital converter. From here, the output can more easily be managed through programs like MATLAB.
As part of our project, we wanted to investigate the state of commercially available MEMS magnetometers. To do this, we took a look at the BM1422 from Rohm Semiconductor. This utilizes the MEMS technology of magnetoimpedance to create measurements. Some important attributes of this device that are similar to ours are its maximum range of plus or minus 1200 microteslas and its magnetic sensitivity of 42 thousandths of a microtesla.
Based on the data the ECE team provided us,
the team performed a thermal analysis on the device to determine how it would react to the heat output from the circuitry. To do so, a heat flux was applied to the silicon layer. We exposed it to 10 and 10,000 watts per meter squared and found that the temperature will remain relatively constant throughout the layers. The temperature of the device was then determined to be 298 Kelvin and 489 Kelvin respectively. The larger the heat flux, the more we have to worry about thermal management. Looking from a broader perspective, we wanted to see if the cold waters would aid in the thermal management of the device. We performed an analysis on the temperature gradient across the autonomous vehicle from the hull to the device. We found that the temperature from the water would not leak through due to the coating of the hull. This would mean that other thermal management options would have to be explored if the circuitry produces too much heat. We researched the packaging methods for the device itself. The 2 primary options being the ceramic and metal as seen in Figure 14 or plastic as seen in Figure 15. We found that the metal would be more costly and could impact the sensitivity of the device. Therefore, the plastic would be better since it is much cheaper and easy to implement due to the simplicity of the device.
An aspect of the vibrational analysis is mounting options, which we summarized in Table 1. The IsoDamp is most comparable to the VersaDamp, which are both screw grommets, and under compression testing, the VersaDamp performed better. Another option is the GMT rubber elastomeric mount, which provides multi-axis protection from shock and vibrations. From our research, we mainly concluded that elastomeric mounts can be produced in a range of rubber compounds and harnesses to suit the application requirements. While working on this project, we performed research on several aspects of magnetometers, including the design and packaging, and created several models. A future project would be able to incorporate all that our team has done by utilizing our thermal models and packaging research to test the functionality of our proof of concept. Thank you for viewing our presentation. We hope you enjoyed it.